It's really my pleasure to give this talk today. And while preparing this talk, I did two things that I should tell you well in advance. One of them is I made the technical part very brief, so well, we can discuss that separately. I think many of you know the technologies already, so I focused on the clinical aspect and the biological need and relevance. And the second thing that I did is to include very last-minute data, so hopefully it will be comprehensible. And I'm presenting this on behalf of two consortia. One of them is COVID-19 and the other one is VASCOVID. I will tell you what they are. So let's discuss a little bit about story of how we actually got into this adventure, because we were not working on anything relevant to this topic when we started. So once the lockdown occurred, we went into our houses. I was in fact working from my garage. You can see my very messy background that became my office. And all our activity in the hospitals has stopped. But we were trying to find some use for ourselves. And the challenge for this was the disease was new. We're talking about March 2020, when people understood very little about the disease. People who knew about the disease were busy. But I had creative postdocs, creative students in my lab, and who are very persistent as well, and with a bit of luck also played into this game, and we got into this. So once we started it, the next challenge to solve was that our labs were closed. Companies from which we can buy components were closed. We didn't have funding dedicated to this. We didn't have dedicated people for this. But we were able to solve this through hours of online meetings. We had some institutional support from ICFO, and we started an ad hoc team to do this. I am telling you this not just because it's a fancy story, but it also taught us a lot of things, how to be ready for future. Then we had another challenge. Our methods, we use them a lot in the clinics, but we never used it in this extremely contagious disease that we could not be in the room. The scenario was very complex. It's the intensive care unit, which was tripled in capacity, maybe multiplied by 10 sometimes. It was overflowing. We couldn't be there. So we had to look for wireless battery-operated commercial devices to do this work, do all our training online, and do everything by audio visuals. This was also a first for us. And of course, in this new field, not knowing anyone in it, everyone being busy, things having to work fast, with no preliminary data, we had to form a network, and we were able to do that. So we formed this consortium. About halfway through my talk, we're going to go back into it. It spans 5 countries. There are 10 clinics in it. The person behind all the medical idea is this guy called Jaume Mesquida. He is a doctor at Partauli Hospital here. He was working 500% of his time was dedicated to dealing with COVID patients, and as he told me once, he would go back home and he wasn't allowed outside to take a breath, take a walk outside. In Spain, the lockdown was so significant, so he said, let me try to do research during this time. So he put this idea together. We are running 2 clinical trials on this aspect. We'll get back to the details. Here I just highlight the fact that apart from one industrial partner, a couple of academic partners like ICFO and Centre for Mathematical Research, everyone else are clinics spread around the world, you know, these things. But why are we even relevant for COVID? Why is this relevant? So these are slides that how Jaume explains this to us. When you are at the critical care, when you are at the intensive care unit with a disease like COVID or sepsis or something similar to like this, there is sort of 2 things that you're trying to do. One is global care. You're trying to restore and maintain tissue oxygenation related to the so-called ABC of oxygen delivery to the tissues. I'll talk about it a little bit more. To keep the person alive, basically, to make sure the whole body functions. Then you have organ-specific care to prevent organ failure. This is the urgency. This is what you're trying to do in the intensive care unit. Okay? But let's look at this global care, the so-called ABC. So on the y-axis here, you see the partial pressure of oxygen in millimeter mercury. And on the x-axis, you see how oxygen moves from air to the cells. And in fact, as a recent review put, oxygen is the most commonly used drug in critical care. Okay, what you see here is that you have the sort of the first level, the so-called A and B, which is the respiratory system. So from air, things have to get into alveoli, get into pulmonary capillaries, and get into arteries. And oftentimes this can be evaluated by a pulse oximeter through the peripheral oxygenation by this little gadget that you put on the finger, which uses light to do this. And then the part C is the cardiovascular system, how this gets into the tissues, and from the tissues, how it goes into the mitochondria. And this is where we come into the picture. So this so-called near-infrared spectroscopy derived tissue oxygen saturation. Okay, so this is the ABC, this is the oxygen trail, which I'm going to revisit a few times during this talk. So this part C is an integration of blood perfusion. That's what gets the oxygen to the given location. Arterial oxygenation, how much oxygen is there, and metabolic rate of the tissue, how the oxygen is being extracted from it. And for example, in resuscitation, which is what you do in the critical care, you want to increase tissue blood flow to meet the metabolic demands, and you need the perfusion and oxygenation to do this. Okay? Where is this normally measured? So they do some local measurements relying on local information, and then you do the hemodynamic monitoring. You rely on the global information, the so-called letter C of this story. Okay? So this picture is also very important, where you measure and what you measure. Okay, I'm going to revisit this as well again. And where is this done? It's often done at the so-called non-vital area. So this graph is not so simple, but basically the point is to tell you that there are two mechanisms. One of them is a global activity, which tries that in non-vital areas, in your arms, in your legs, to constrict the vessels, to direct blood flow to the vital areas, okay? And on the other side, locally, you're trying to dilate them because you're saying, oh, my hand is not getting enough oxygen, okay? These activities are limited on organs like skin, moderate on organs like the skeletal muscles, and very efficient in the brain. 90% of my research, I talk about the brain and autoregulation, but in this particular case, we got into the skeletal muscle business and looking at how this complexity of these two mechanisms is working. But where does photonics come into play here? I'm going to be talking about two technologies here. We call them hybrid diffuse optical monitoring and imaging. One is near-infrared spectroscopy, uses near-infrared light to measure blood oxygen saturation 1 to 2 centimeters below the tissue, and it does it locally at the microvascular level. For example, you can go to the brain from outside, or you can go into the muscles. And the other technique I'll talk about is diffuse correlation spectroscopy, which allows us to measure blood flow. And this is the only technical part I will tell you today about, because I think LaserLab members can follow this very easily. So when you shine light into a turbid medium, such as tissue, in about 100 micrometers, you start having light scattering, mostly in the forward direction. By about a millimeter of path length, you enter the random walk regime. At this regime, you don't know where the photons originated from. What we are interested is to look at tens of centimeters of path lengths in tissues, and the absorption length is about 10 centimeters in the tissues in these wavelengths. Okay, so we have multiple scattering and absorption. Scattering occurs every time the index of refraction changes, and one of the places this occurs is the mitochondria and the nuclei, and also the cells. And the absorbers are blood, water, lipids, and collagen. And this is where the main difference between deep tissue diffuse optics and microscopy happens. So if you look at this picture, what I'm showing is that you can put a light source and the detector on the same side of the tissue, for example, on my arm, and the light will do multiple scattering, and it will come out from the same side. And after these thousands of scattering events, I can detect it. And if I can separate absorption from scattering in a reliable way, I can get information about the tissue. Okay? This works because if you look at the spectra, absorption spectra, here the y-axis is logarithmic. It's the absorption coefficient, so inverse of the absorption length. What you see is that there's actually about 2 decades or 3 decades less absorption in the so-called near-infrared range, 650 to 950 nanometers. And the oxyhemoglobin red line, and deoxyhemoglobin, blue line, have differential absorption. If there was no light scattering, we could do simple spectroscopy here. But with light scattering, we have to work a bit more complex. We can discuss what you can do in the visible, what we can do beyond the visible about the micron. These are very interesting technical discussions, but let's stick to this picture for now, because as I said, I'm going to talk more about the clinical applications. What we do in my lab is we analyze all these using this photon diffusion model, which relates the photon fluence rate, its temporal evolution, and how it changes in position to these parameters, such as the photon diffusion coefficient D, which contains the reduced scattering coefficient, and mu A, which is the absorption coefficient. It's a very practical, it's a very solvable model, and it was a revolution in this field about 30 years ago to start to use it. But there's more to lights. Laser lab, the laser means we know about lasers. And as you know, the lasers have speckles. The speckles fluctuate. And it so happens that if you choose your laser correctly, even after these tens of thousands of scattering events, we still have speckles. And then one way to quantify their statistics is to put a single mode fiber and detect their fluctuations and calculate the intensity autocorrelation function that I saw here. And what you see here is the red dots are real data, and blue line is a fit, that if you have enough photons, and we're talking here about 10,000 photons per second, so we take data in sub-second time intervals to get reliable measurements, we can use another diffusion model, so-called the correlation diffusion equation model, which is the diffusion of these autocorrelation functions through the tissues, and fit this data and obtain the parameters I was telling you. Okay, but as I mentioned in the beginning, when we got into COVID-19, we had to work with what was available in the market because we couldn't go to ICFO and build our fancy devices or steal 12 devices and send to different centers. So this technology, the NIRS, exists as FDA CE certified devices and research devices that you can buy. It turns out we couldn't buy any FDA CE certified ones, but we could buy research ones. But how could this be useful? The clinicians, it turns out, there was a whole world of clinicians using this with a so-called vascular occlusion test. What they wanted to do is to look at this peripheral oxygenation, non-vital organs, to learn about diseases in the intensive care unit. They would put an arm cuff. They would put one of these probes on the thenar muscle or on the arm, and they would inflate the cuff beyond the systolic pressure, which would cause the blood flow to cease into that region. And from the baseline value of oxygen saturation, you could evaluate baseline metabolism. From how fast the tissue deoxygenated, you could look at the metabolic status of tissue because we are blocking both input and output flow. So tissue is alive and it's consuming oxygen. And when they release it, they could look at this hyperemia, this increase in oxygen saturation beyond the baseline, and its height to look at evaluate endothelial function and microvascular reactivity. And the doctors were telling us that, wow, this is really cool. We used it in the past in mixed ICU patients, in septic shock patients, hemorrhagic patients, in weaning from mechanical ventilation, because it could allow them to detect early tissue hypoperfusion and evaluate its persistence. Okay? So we want and evaluate endothelial function. These things are a bit too much for non-medical audiences. Let's look very slowly. So if the oxygen saturation is low, patients are hypoperfused, this was shown to have a very high prognostic value. At the moment, it was mostly a research activity because there was no standardization and no progressive prospective trials. Deoxygenation impairment indicated tissue was not able to use oxygen, and that also had a good prognostic value. And the reoxygenation showed endothelial dysfunction, and that had even more prognostic value. And that allowed the doctors to think about hemodynamic interventions, new treatments, etc. So while they were discussing this, they were publishing papers, and to be honest, they were not coming to our conferences, so I was not even aware of it. But they were excited about it. So let's take a look at a few examples from their literature. In this particular paper published in 2007, they looked at septic patients. These patients are in a very horrible condition. It still is a deadly disease and with a high morbidity. Oops, I leaned back too much. And they showed that altered recovery of muscle tissue oxygenation after this VO2 oxygenation was quite frequent, and it was related to severity of the disease, and it was prognostic. It was associated with a worse outcome. What does that mean? That means that if this is shown in prospective trials, the doctors could take different actions in septic patients. In ARDS patients, patients with acute respiratory distress syndrome, we're going to look deeper into this because that's what COVID does to patients. It was altered early, and it was determinant of the outcome. Okay. And finally, a work by Jaume Mesquida, our collaborator, he showed that extubation failure. So when you come out of these ventilators, we heard about ventilators day and night during early days of COVID. There weren't enough ventilators. People were inventing ventilators in their homes by 3D printing them, etc. All these things were also related to this oxygen saturation related things, and it was predicting extubation failure. Let's look a bit deeper. Let's start with ARDS. It's a hypoxemic respiratory failure because the lungs are basically inflamed. This is precisely what is done by COVID. So what happens is that your heart is at that moment working fine. Your lung thinks it should be working fine. Blood is getting to the lungs, but your alveoli is filled with stuff due to this inflammation, and you can't get oxygen to come into your bloodstream. And oftentimes its severity is measured by the amount of oxygen you breathe and the ratio of the arterial oxygen saturation you have in your hands. Okay, organs get oxygen deprived and people start to die. And already people used to say that there were many places where there could be better things. Some could work for prevention of ARDS, some could work for understanding where somebody will get to ARDS, when to intubate them, and then during ARDS when they can be taken out of ventilators, etc. And during the early days of COVID, when thousands and thousands of patients had to be ventilated and were showing up with ARDS, they had no clue how to deal with them because standard protocols were failing. Okay? They were looking for novel approaches to target one aspect of the pathophysiology with these things. And this study that I quoted earlier has found that this ascending slope, so what happens after you release the occlusion in the muscle, measured by optics, was shown that it was decreased in patients with poor ARDS evolution. I hope you can see my pointer, the third box plot on the left graph. And the people who died also had showed impairments in this. Another third box plot on the right graph. Okay. And if you try to do an ROC curve to predict poor evolution and mortality, it did much better than how you do in the clinics using the clinical parameters. And as I said earlier, while this result was very interesting and very important, it has never been done in prospective trials to alter what's happening, and that was because the NIRS devices were not standardized. Next thing is the weaning from mechanical ventilation. As I said, before COVID, people were mechanically ventilated, and even people who went to the point of spontaneous breathing trials, which is what is shown in this complex, difficult graph, is that when someone is mechanically ventilated, unlike what you see in a TV series like House, where he walks into the room and pulls off the pipe and the person says la 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 and starts to speak and turns back to life, extubation is a much complex procedure. Mechanical ventilation is horrible for the person. Okay, so they basically let the person try to breathe on his or her own, and they decide. And if the person can do it in one go and they can extubate, it's called simple. If it's more than 3 times, it's very complex, and if more than 3 times it doesn't work, this person may never come out of weaning and may never speak again, even though a person may survive. It's a horrible scenario. And even after this spontaneous breathing trial works, 20% of the patients show extubation failure. Urgent moves are needed with a predictive power. People are using machine learning, and many methods are being utilized. Okay. The problem is there's cardiovascular insufficiency to cope with the increased cost of breathing. Everything has a cost. When I breathe on my own, my body consumes more oxygen compared to a ventilator. And when that happens, peripheral areas are hypoperfused due to those mechanisms I showed you earlier, because blood is directed to the vital areas, and slowly organs start to fail. And the question was, can NIRS, this optical method, be used to predict this? And what was shown is that this deoxygenation slope, how fast you deoxygenated, was reduced in patients with extubation failure 30 minutes into spontaneous breathing trial. And those who failed also showed a poorer ratio in this thing compared to the initial one versus the 30-minute one. So once a little bit of time has passed on spontaneous breathing, this was altered, and this method could predict extubation failure. And that's extremely important and useful, okay? And they were able to come up with a complex score called the STO2 score, all coming from optical measurements, and proved that blood flow was diverted from periphery, and that diversion was not working well due to endothelial dysfunction. Okay, and the question is, can we translate to the clinical practice? Okay, so this is where the literature was. There was evidence that this technique could work, but there was nothing that showed that it was ready to be used in the clinics. So how is this relevant to COVID? Okay, this is a paper from April 2020 from Science. At that moment, many people were talking and saying that COVID is a disease of the lungs, and they are trying to save the lungs. They are putting people on these ventilators, but the evidence was immediately starting to form, and now we understand this much better, that COVID attacks all over the body. And as you see, the second point is heart and the blood vessels. Okay, in fact, it targets the lining of the blood vessels where there's a certain receptor, and if I go into the depth of this, I will fail to explain it, but endothelium is affected. So if you can measure endothelial dysfunction, in addition to all these other things I told you about what happens to patients in ICUs already, there should be some value for this. So there's even additional ideas that the infection of epithelial cells increases as the severity of the disease increases. It leads to coagulopathies, so the blood clots and everything. So hemodynamics, oxygenation, and everything is working, and the mechanical ventilation is a common process. So we approached Jaume, and as I said, Jaume said, yes, I have been working on this topic and it's of interest, even though it's not yet been proven. This was in March 2020, few weeks into lockdown, and he said, let's put this together. And we came up with this idea. It's the biggest clinical trial that my lab has ever been involved in, where we said we want to get 400 COVID subjects, 400 ICU non-COVID subjects, and 400 healthy control subjects from these 10 centers. And we're going to do this with this vascular occlusion test with an NIRS device placed on the forearm. You see this location that I show in this graph. In the earlier graphs, I showed the thenar muscle, this big muscle near the thumb. And that's because the only device that was available at that moment that we could lay our hands on was these little devices by a company in the Netherlands called Artemis, and that only fit on the forearm. We would have liked to do it in the thenar muscle, but that's okay. But we were able to secure a dozen of these devices, and we were able to run a complex training remotely, mostly operating devices from the homes of our students, entering ICFO with special permissions, etc. It was interesting times and challenging, but we did it. And we had 3 objectives in the first part of the study. Part of it is published in the paper you see below. And let's go through them. So the first was healthy versus COVID-19, and we're going to look at the published results. So COVID-19 patients and healthy controls. So healthy controls are not really good controls. We're going to look at non-COVID-19 patients later on, but until quite recently, non-COVID-19 patients were not quite accessible for us because COVID patients were dominating the ICUs. Okay, so there are some limitations to what I show you, Nevertheless, if COVID-19 patients show impairments, and if this is related to outcome, intubation, extubation failure, etc., it doesn't matter whether it matches the controls or not. Okay? So I'm going to show you results from the 73 patients. So as I remind you, I show you this vascular occlusion graph. We're going to look at the baseline oxygen saturation. And what we found out that the baseline oxygen saturation didn't differ between controls and COVID-19 subjects. COVID-19 subjects were mostly ventilated here, so that makes sense. But the deoxygenation slope, so this aspect which measures the metabolism in a more reliable manner, was reduced in COVID-19 subjects. So they showed impaired metabolism. They were consuming less oxygen compared to the controls. And when we looked at the reactive hyperemia, both the area under the curve and the hyperemic peak were reduced in the COVID-19 patients, which meant they had an impaired endothelial function. So far, that's common to ARDS patients as well. It's good, it's motivating. This is about the 1/4 of the study population that we aim for, and we were able to get these results. So how does it compare to other ICU patients? Does it have any clinical relevance? I cannot tell you. That's to be determined with the continuation of the study. Next question we asked is sedation versus non-sedation. Patients who are under mechanical ventilation are sedated, and sedation could, of course, alter these parameters on its own. So we looked through our data and we saw that 39 were sedated under mechanical ventilation, 34 were in non-invasive respiratory support, and they were not sedated. Okay? And then what we showed is that invasive versus non-invasive, sedation versus non-sedated, check mark versus X, there were no significant differences between these 2 points. So that showed that the effects that we show in the microvascularization are not due to sedation, but they are most likely due to the condition itself. Then we moved on and looked at the ARDS severity. As I told you earlier, ARDS severity is normally measured between the amount of oxygen in the arterial blood and the amount of oxygen the patients are breathing. Okay, here we didn't have arterial blood growth in every center. Remember, we have Mexico, Brazil, US, Italy, and Spain. This is an unfunded study ad hoc in an emergency situation, so not everything is equalized in all centers. So we used the SpO2, which is the pulse oximeter value measured on the fingers. And what we saw is that the severity of the disease meant, again, low air oxygen utilization in the baseline and endothelial dysfunction reduced reoxygenation slope compared to the mild cases. This is also very similar to the preliminary data I showed you. So it's related to the severity of the disease at that moment. Okay? So this is what was published so far. Now I show you some what I call hot out of the oven data. This is new data with an increased data set analyzed a couple of days ago. And I'm looking at mortality, so prognostic utility. First of all, non-survivors had a different results in their clinical findings, but they also show lower amount of blood volume, so possibly reduced perfusion at the baseline condition, this THD shown in red, and also they showed reduced hyperemia, impaired endothelial function at that moment. So this data is extremely interesting as well, because endothelial impairment correlates with mortality, like we saw in the other populations in the previous studies. But is it even relevant to what was done to them? Looking at this early data, where a lot of things were done ad hoc, one common thing is the use of this drug called remdesivir. So once we mine the data a bit, 112 subjects had no remdesivir, 18 had remdesivir treatments. Remdesivir subjects in particular had higher total hemoglobin concentration in the baseline and higher hyperemia. So the question is, did it actually improve microvascular health? What's interesting is remdesivir also improved, reduced mortality as well. So it did its job. It helped our patient population. And it also improved microvascular health. Were the two related? I do not know. This is hot out of the oven data. Most of our analysis for this part of the study will always be prospective, looking and figuring out what happens, etc. What are the associations, but it will allow us to look forward. But so far, what I'm telling you is that what was in the literature held for COVID-19 patients, it does appear to be health prognostic value. It is related to some amount of treatments they have received, so it's interesting. So our hypothesis is that this should allow stratification derived from endothelial function evaluation to treat patients in different ways, maybe take more aggressive, do have some aggressive treatments. Perhaps if this was available in the start of the pandemic, it would have been quite helpful because the resources were limited. But in the long run, also there are treatments targeting endothelial function. And what was realized in the earlier clinical trials was that they might not always be beneficial because of lack of appropriate selection of patients. So if we can select them well, it should help. And then the other part is the rescue ventilatory strategies. Another thing we heard in COVID is that you lay a person face down on a bed helps COVID patients. But these things are also not so easy, not so comfortable. They come with certain problems. And the second part of our trial, which we haven't yet analyzed the data, is actually look at the effect of this prone positioning. You can look at our hypotheses and details on our clinicaltrials.gov registration. And also this leaning from mechanical ventilation support. This is extremely, extremely interesting and relevant for this disease. All good so far, but what is missing? Let's go back to this ABC of oxygenation. Remember I said that we are interested in what happens at the tissue level, at the cardiovascular system. And what I said is we can look at tissue oxygenation by so-called this NIRS STO2. This is the oxygen saturation in the microvasculature locally. But I also said that this is the integration of blood perfusion, arterial saturation, and metabolic rate. And besides that, what's done is to increase blood flow to meet the metabolic demands. But we are not measuring perfusion right now. We are missing this with these methods. This is not available. We cannot buy these devices that does this in any easy way. You can buy from our spin-off companies research devices. But remind you, what I told you in the beginning is that we actually have two techniques, NIRS and DCS, that would allow us to measure blood flow and oxygenation together. Besides that, there's also another problem. Clinically available devices, some of which you see in the pictures, and also the ones we use on the research, work very well to measure as trend monitors. And they are very well validated in some settings. That's why some of them are CE and FDA approved, but they fail in others, and tissue heterogeneity is a major problem for them. And that happens due to very simple physics. The top graph here shows you what you would do in a simple spectroscopy experiment. You have a medium, you know the path length of the light, you shine the light, you go to a distance, you look how much the intensity has reduced, all the losses are due to absorption, you can do absorption spectroscopy, no problem. But if I do the same in tissue, where what happens is what you see in the circle on the below, where there's multiple scattering all over the place, you don't know the path length, and you don't know whether you lost the light due to absorption or scattering, whether some of it got scattered to other parts or it was simply lost due to absorption. So these CW devices inherently cannot separate these two effects, and the accuracy suffers. And if you cannot resolve the path length, you cannot separate what is superficial versus depth. Look at your muscle on your forearm, for example. Above it, I don't know if you can see my video properly. You see that there's a whole layer of this is what I'm holding here of fat over my muscle. How can I separate this from another person with a bigger muscle or a bigger fatty layer? There are exotic ways of trying to deal with this, fancy physics and algorithms, but it's not so good yet. It works for certain purposes. In our field, we tend to use traditionally 3 different light sources. One is continuous wave, other one is brilliant physics. We amplitude modulate the light at megahertz to gigahertz and create diffuse photon density waves. And the other one is to use pulse light. So here I talked about continuous waves so far, but in our labs and in our colleagues' labs, other laser lab partner, Politecnico Milano, Polimi, they use pulse light sources. So you put an input light source and you look at its broadening. Problem with the other types is they tend to be more expensive and more complex. But hey, we are laser lab. We are developing research. We can work with TCS, PC electronics and such. So we have been doing it many years, and these techniques are getting slower. So in this case, we put picosecond sources, let's say 100 picosecond source. We use photon counting detectors. We use a time correlated single photon counting, and then we separate resolve within path length. It broadens to many nanoseconds, so meters of photon path lengths. And we can resolve that. We can separate absorption from scattering. We can discuss the physics and the light sources in details later. Okay? And we can put this technique together with diffuse correlation spectroscopy, which is what I told you earlier with the spectrum. And when you put that together, you get deeper into what the doctors wanted. You can get at a parameter called metabolic rate of oxygen extraction. In the brain literature, this is known as the CMRO2. In the muscles, we call it the MMRO2. Basically, it says that on the arterial and venous components, if you look at the difference of oxygen between that and compare it, how much you're delivering, the blood flow, you can get at the rate at which oxygen is extracted, which is in turn related to the oxygen metabolism of the tissue. And if you play a little bit with models, assume steady state conditions, compartmentalization, etc., this could be another whole talk. You can relate these parameters to the peripheral oxygen saturation that you can measure with a pulse oximeter, easy. STO2, measure with an IRS, everything I've been showing so far. And blood flow measured by DCS. So now we can actually relate perfusion and oxygenation at this component C that the doctors wanted to look at, what was on the bottom part of this slide. So where am I getting at with this story? Somewhere mid-2020, European Union put under the Horizon 2020 scheme a call for urgent applications to develop devices dedicated to dealing with the COVID-19 pandemic. And we put together a consortium involving two laser lab partners, ICFO and Politecnico Milano, a startup company from ICFO, Hemophotonics. My disclaimer, I don't earn any money through Hemophotonics. I do not have any financial relationship with the company. My conflict of interest is monitored by ICFO's KTT unit. All medical talks should have this. The spin-off company of Politecnico Pioneers. These are crucial if we ever want to move this to the clinics. A Dutch company called Splendo, an Irish company called BioPixS, involved in standardization. Splendo is involved in artificial intelligence and remote control, and the local Spanish company involved in regulatory affairs, because we want to translate this to CE certification and the clinic. And what we are building is combining this time result NIRS, time domain NIRS, and diffuse correlation spectroscopy to get locally at these measures, adapt the device and the probe to where we want to measure on the peripheral muscles, include an automatized tourniquet to induce this VOT exercise, use machine learning and remote control and cloud computing to make this compatible with everything that happens in the ICU, and include from the beginning regulatory approval processes. So this is the current prototype that's entering clinical testing in Partauli. It's a 19-inch 4U rack, so it's relatively small. Those of you who know our earlier devices know that we often work with refrigerator-sized devices. It is fully incorporated. It's battery operated, so even if we go back to the COVID-19 status where doctors have to run it from far ahead, they can operate it with an iPad. They can also operate it on the screen. We have come up with a fancy probe, which contains not only the fiber optics for our light sources and detectors, but multiple levels of safety provision. So the laser light cannot get into the eyes of the operators, and it can be left with the subject. Everything is automatized, and we are documenting it to be CE certifiable. The project timeline, it's an extremely challenging project for us. We are in month 15 now. and it will finish at the end of this year. The goal is to end up with a device with the documentation to, once new further funding is released, to send it for CE marking, and also have funding of enough clinical relevance from about 100 subjects, so future clinical trials can be made to actually show efficacy. New adventure for us. We normally do this type of projects on 4 or 5 year timelines and without all the issues with visas, recruitment of people, etc. But it's also super exciting. We can discuss technical issues of this device later on. There's a lot of potential for collaboration with laser lab partners in different sources, detectors, and different application areas as well. And before I end, I should also show you that this has been also a very bumpy and amazing ride, because we didn't stop there. We also used our existing brain devices while they were sitting at ICFO to show, for example, that surgical masks do not alter brain function in healthy people. But for example, if you are using masks on our subjects when we do neuroimaging or neuroscience, those results are affected. We published this in TNAS. We are working with NIH to see if we can make a low-cost, ultra-portable version of this VASCOVID device by sort of giving up on precision, but making it more widely available. That's an R21 project with colleagues from Texas. And we have recently been funded locally to look at long COVID-19 patients. And I have to stress that we want to do this with open science. We want to collaborate to make this widely available for COVID-19 patients, so all our data and everything is widely available. And finally, some advertisement, acknowledgement of many grant funding. These are not all funding the COVID work, but everything I show you here, the only reason they could happen so fast was because we had a lot of experience and we are hiring. So I'm open for questions. Thank you for your interest. I hope I was not too fast to complicate it. Thank you.